The German Schwere Gustav railway gun was an 800mm monster that needed 2 parallel tracks just to turn its barrel. It fired a 7-ton shell exactly 48 times across the entire war, a logistical nightmare that barely justified its existence. But compared to the machines in this list, that over-engineered cannon was a model of practical engineering. Today we are looking at 7 aircraft that defied aerodynamics so completely that their creators should have been charged with crimes against physics. The Hughes H-4 Hercules was a wooden flying boat the size of a football field, built to carry 750 troops over the heads of German submarines. Howard Hughes poured $23 million of wartime government money into it, then personally strapped himself into the cockpit for a taxi test that unexpectedly lifted off the water. 26 seconds later, the Spruce Goose settled back down and never flew again. That single hop was the high point of a program so absurd that Congress hauled Hughes before a committee just to ask where the money went. Before we begin, tell us in the comments where you're watching from and subscribe so you make it to the #1 spot where the loudest disaster waits. Now, let's start the countdown. Christmas bullet. In the final months of World War I, a Washington physician named William Whitney Christmas arrived on Long Island with no aeronautical training and a design for a fighter plane. He persuaded Continental Aircraft Company to build it, dangling an outlandish scheme to kidnap Kaiser Wilhelm II. The U.S. Army lent a prototype Liberty 6 engine producing 185 horsepower on the strict condition it would only be used for ground testing. Christmas ignored that. The aircraft was an all-wood cantilever biplane with a 28-foot wingspan, weighing just over 2,100 pounds fully loaded. Its defining feature was the complete absence of struts or bracing wires between the wings. Christmas insisted the wings should be flexible, deliberately designed to flutter in flight. Wing warping would provide roll control, a method already obsolete by 1918. The chief engineer, Vincent Bernelli, recognized the danger immediately. Without rigid bracing, aerodynamic loads on a cantilever wing create enormous bending moments at the root. In a flexible structure, flutter sets in when airflow couples with the wing's natural frequency, rapidly building oscillations that exceed the material's strength. The wood was salvaged scrap, not aircraft grade, so the safety margin was already compromised. Christmas claimed a factor of safety of 7, a number with no basis in calculation. In January 1919, the bullet took off on its maiden flight. The wings peeled away from the fuselage. Test pilot Cuthbert Mills died in the crash. The destroyed Liberty engine was never reported to the Army. A second bullet was built with a Hall-Scott L6 engine and displayed at Madison Square Garden in March 1919 as the first strutless airplane. It too crashed on its first flight, killing Lieutenant Allington Joyce Jolly. The project was abandoned before any military evaluation. Christmas spent the rest of his life claiming he had sold the wing design to the U.S. Army and held hundreds of aviation patents. None of it was true. Fisher Pice 75 Eagle. In September of 1942, General Motors received a directive to build a high-performance interceptor. The concept was to combine the best existing components from different aircraft into one super fighter. Outer wing panels came from the Curtiss P-40 Warhawk. The tail assembly was taken from the Douglas A-24 dive bomber. The landing gear was borrowed from the Void OIF-4U Corsair. All of this was mated to a central fuselage, housing the massive Allison V342 O24-cylinder engine placed behind the cockpit and driving coaxial, contra-rotating propellers through an extension shaft. The promise was a wonder plane capable of an extremely high rate of climb. The press coverage was extensive before a single prototype had flown. When the first XP-75 took off on November 17, 1943, the reality proved to be a fundamental failure of integration. The amalgamation of parts created a machine with a miscalculated center of mass. The heavy midships engine and the complex drive shaft pushed the center of gravity into a position that made the aircraft inherently unstable. Spin characteristics were described as poor. High aileron forces at speed made the controls dangerously stiff. The engine, rated at 2,885 horsepower, failed to deliver its expected power and consistently overheated due to inadequate cooling. Redesigns were ordered. A modified tail assembly, a new bubble canopy, and a corrected engine variant were rushed into the long-range prototypes. But by the time the first production P-75A models entered flight testing in September 1944, the war had moved past the need for this type of aircraft. The Lockheed P-38 Lightning and the North American P-51 Mustang were already performing the long-range escort role with proven excellence. There was no rational reason to inject a new, unproven type into a supply chain already running at peak efficiency. The production contract for 2,500 aircraft was terminated on October 6, 1944. Only 8 experimental prototypes and 6 production models were ever completed. The airframe left sitting in the experimental hangar was a testament to the flawed premise that a great fighter could be assembled from spare parts. Body 152. In 1955, East Germany bet its aviation future on a jet airliner designed by former Junkers engineers who had just returned from the Soviet Union. The project was led by Brunolf Body, and his team effectively had to redesign the aircraft from scratch in Dresden. The result was a 57-seat, 4-engine jet with a fatal aerodynamic identity crisis. The landing gear was borrowed from a bomber. The main gear was housed along the fuselage center line, with outrigger wheels at the wingtips, a configuration copied directly from the Boeing B-47 Stratojet. For a high-wing passenger plane, this meant the aircraft's center of gravity was dangerously high and its track was extremely narrow. Ground stability was poor, and any asymmetric loading during landing risked a wing strike. The first prototype also kept a glazed navigator's nose, a feature from its bomber ancestors that created drag and served no purpose on a civilian airliner. On March 4, 1959, during its second flight, the prototype entered a stall and crashed at Ottendorf, Aquila, killing the entire crew. The pilots, inexperienced with jet engines, likely could not compensate for the slow throttle response of the early turbojets. A sudden power demand during a critical low-speed phase would have caused an unrecoverable loss of lift. The investigation was never fully completed. A second prototype flew in 1960 with a revised landing gear and indigenous Purna 014 engines, but the test program was terminated after just 3 flights. A design flaw in the fuel system interrupted the supply during steep descents, a problem that may have contributed to the first crash. By February 1961, the East German government dissolved its entire aeronautical industry under Soviet pressure. All 3 airframes were scrapped. The 30 completed Purna 014 engines were later bolted onto East German minesweepers. Tupolev Tu-144. In December 1968, the Soviet Union did what seemed impossible. It put a supersonic airliner in the sky before the British and French. The Tu-144 prototype lifted off from Zhukovsky Airport on the last day of the year, beating Concorde by 2 months. The rush was no accident. Nikita Khrushchev's directive was blunt. Leapfrog the West. The Tupolev Design Bureau, led by Alexei Tupolev, was ordered to build 5 flying prototypes in 4 years, with the first ready by 1966. The result was an aircraft that was bigger and faster than Concorde, capable of Mach 2.15, but speed came at a cost. The engines were the first problem. The Kuznetsov NK-144 turbofans burned fuel at a cruise rate of 1.58 kilograms per kilogram of thrust per hour, far above the required 1.2. This gave the Tu-144 a range of only 2,500 kilometers, less than half of Concorde's. To keep the aircraft supersonic, the afterburners had to run continuously in cruise, a brute force solution that made the cabin deafeningly loud. Passengers could not hold a conversation without shouting. The noise came from the engine intakes, which were twice as long as Concorde's, based on a Soviet misconception that extra length would prevent surging. It did not. The real structural danger revealed itself on June 3, 1973, at the Paris Air Show. The Tu-144 entered a steep dive during a demonstration, pulled up so violently that the airframe exceeded its design limits and broke apart in midair. The left wing tore off first, then the fuselage disintegrated. All 6 crew members and 8 people on the ground were killed. The cause remains debated, but the official Soviet investigation pointed to a French Mirage fighter flying too close, forcing an evasive maneuver that overstressed the airframe. The aircraft simply could not handle the G-forces. After the crash, only 55 passenger flights ever took place. The Tu-144 was withdrawn from service in 1978 after a new variant crash-landed during a test flight. The program limped on as a cargo carrier until 1983, then ended for good. Bochum BA-349 Nader. By the autumn of 1944, the Luftwaffe was being systematically dismantled over its own cities. Conventional fighters needed runways, and runways were bombed to rubble. The Nader was a response to this collapse, a manned surface-to-air missile that required no airfield at all. It would launch vertically from a steel tower, guided by autopilot toward the bomber stream. The pilot would take control only for the final seconds, fire a salvo of unguided rockets from the nose, then dive away. After the attack, the entire nose section was jettisoned. The pilot would then unbuckle, pull a release, and be thrown forward out of the cockpit by his own momentum to parachute down separately from the fuselage. The Walter rocket engine burned a mix of T-stoff and C-stoff, generating 1,600 kilograms of thrust. 4 solid fuel boosters strapped to the rear added another 4,800 kilograms for the first 10 seconds. The airframe was built from glued and nailed wood by unskilled labor. The concept was desperate, but the physics of the escape sequence contained a fatal assumption. The pilot was supposed to exit the cockpit after a high-speed dive, at which point the aircraft would decelerate rapidly thanks to a braking parachute, flinging him clear. This relied on the cockpit canopy, releasing cleanly at the right moment. On March 1st, 1945, test pilot Lothar Sieber strapped into the only manned vertical launch ever attempted. The Natter roared up the 20-meter tower and climbed for roughly 1 minute. Somewhere in that minute, the canopy detached prematurely. Sieber likely lost consciousness immediately. The aircraft continued under autopilot, reaching an altitude of perhaps 1,500 meters, before arcing over and plunging into the ground near Stettin am Kalten Markt. The entire flight lasted about 60 seconds. No operational missions were ever flown. The Natter never fired a shot in anger. After the war, captured airframes were shipped to the United States for evaluation and quietly scrapped. Northrop X P-79. In 1942, Jack Northrop envisioned a fighter that could destroy enemy bombers by physically slicing through their tails. The United States Army Air Forces issued a contract in January 1943 for a magnesium-armored flying wing designed to withstand the impact. The pilot lay prone in the nose, a position meant to let him survive the extreme G-forces of a high-speed ramming attack. The initial design used a 2,000-pound thrust rocket motor running on red-fuming nitric acid, but that engine was so problematic it was scrapped. The sole prototype, redesignated XP-79B, was fitted with 2 Westinghouse 19B turbojets producing just 1,150 pounds of thrust each. The aircraft was built from welded magnesium alloy, a difficult and brittle metal that made the structure a nightmare to repair. Its control system was a unique experiment in aerodynamics. There were no rudders. Instead of traditional control surfaces, the XP-79 used a bellows-boosted split elevon system. Air intakes at the wingtips fed these split flaps, which opened asymmetrically to increase drag on one side, forcing the aircraft to yaw. This created a fundamental instability, trading positive control authority for a theoretical reduction in drag. The pilot steered with a tiller bar, managing an untested aerodynamic scheme with no margin for error. On September 12, 1945, test pilot Harry Crosby took the XP-79B up from Muroc Dry Lake. 15 minutes into the flight, during a slow roll, control was inexplicably lost. The nose dropped, and the aircraft entered a vertical spin, corkscrewing into the desert floor. Crosby attempted to bail out, but was struck by the spinning wing and killed. The project was canceled immediately. The second prototype left unfinished. The magnesium flying wing had been too radical, its aerodynamics too unstable to survive a basic maneuver. Hughes H-4 Hercules. In 1942, the U.S. War Department faced a crisis. German U-boats were sinking Allied shipping in the Atlantic at an alarming rate. The solution, proposed by industrialist Henry J. Kaiser and aircraft designer Howard Hughes, was audacious. A flying cargo ship built entirely of wood to bypass wartime restrictions on aluminum. The contract called for 3 prototypes, but only one was ever completed, and it flew just once. The aircraft was a victim of its own monstrous scale and the fundamental conflict between buoyancy and aerodynamics. A flying boat must lift its hull clear of the water to reduce drag and achieve flight. The H-4's hull was enormous, over 5 stories tall, with a wingspan of 320 feet, longer than a football field. To break free of the water's surface tension and suction, it needed immense power. Its 8 Pratt & Whitney R436-0 radial engines, each producing 3,000 horsepower, were theoretically sufficient. But the wooden construction, though innovative, added weight. The Duramold process laminated birch veneer with resin, creating a structure that was strong but heavy. The aircraft's empty weight was over 250,000 pounds. When fully loaded with its intended payload of 150,000 pounds, 2 30-ton M4 Sherman tanks, or 750 troops, the wing loading became critical. The massive wings, with an area of over 11,000 square feet, had to generate enough lift at relatively low takeoff speeds. Ground effect, the cushion of air trapped between the wing and the surface, helped it lift off briefly. On November 2, 1947, during taxi tests with Hughes at the controls and 36 people on board, the H-4 rose 70 feet above the water for 26 seconds, covering about 1 mile at 135 miles per hour. It never flew again. The single flight proved only that it could skim in ground effect, not that it could sustain altitude with a payload. The aerodynamic flaw was inherent. To carry the required load, it needed more lift, which demanded even larger wings, adding weight and drag in a vicious cycle. The project cost $23 million, equivalent to $253 million today, and was obsolete by war's end. The military no longer needed a transatlantic transport immune to submarines. The Spruce Goose, as critics dubbed it, was mothballed, maintained in secrecy by a crew of 300, then 50, until Hughes's death in 1976. It survives as a museum piece, a monument to a brilliant but misguided vision. Aerodynamics punishes hubris with a simple equation: drag always wins. If you enjoyed this video, leave a like and subscribe to the channel. Drop your idea for the next episode in the comments.